Okay guys, in section 6.2 we want to find the region or the area between curves. And so the idea would be to take two curves, let's say f of x, and then another curve g of x, given here, and find the area between the two of them. And then something even more interesting that we can do is we can take this guy and we can rotate it around an axis, find volumes, or do all kinds of crazy things with it. So again, in this section, we're just trying to find the area between the first curve and a second curve. So what you'll notice here is that to find the area between the two curves, what I'm going to do, and this is kind of just fun to play around with, but what I'm going to end up doing here is taking the area between them and dividing it up into a whole bunch of little rectangles. Okay, just like we would do with the Riemann sum. And so you can go ahead and you can play around with these. So you can set your initial point, or initial starting point, your initial x value, your end value, and then we can change the amount of rectangles, the number of rectangles that we have under there. And what you'll notice is that the approximation given by the sum of those rectangles is fairly poor when there's very little or very few of the rectangles. Because look, like right here, you're missing all this area, you're missing this area, this guy right here, you're missing some area over here, and you've overcounted area here and here, over here. But as we increase the number of rectangles, the amount over and the amount under becomes much more, it becomes less as far as the difference between them, and we end up with a much more accurate picture of the area. So you should have probably talked about stuff like that in Cal 1. The book goes through some animations here for doing the sum and setting it up. So they give this, and then they go to the part that's most important here, and that's going to be your formula for the area between two curves. And what you have to do is you have to take the difference between the two functions and then integrate that over the interval. Okay, and so they go ahead again. You can go through and play with some of these animations, and you can see those calculations occurring. What I'm going to do is this problem right here. Okay, so I'm going to find the area between this line, x plus 3, and this curve right here, which is the absolute value of 2x. So let's go ahead and draw that out. So we'll get a sketch of it again. And so we have the absolute value of 2x, which I'll do here in green. Close enough. And then we've got, what was the other one? 3x. Let me go back and check to see. X plus 3. Okay. And so x plus 3 will start up here at a height of 3. But the slope is a little bit flatter, so it's going to look maybe something like that. And what we want to find is this area in between the two curves. So here's the idea. Here's the picture that's going on here. What we're going to do is we're going to find the area underneath the yellow between the following two. So I'm going to, from this guy, which is our A value, and over here, this is our N value, our B value. What we're going to do is we're going to take the area underneath the yellow. Okay, so I'm going to redraw that for you. What this is going to look like is I've got the yellow curve that looks something like this, and I've got A, and I've got B, and I'm going to take the area underneath that. So let's let this guy be f of x. So this thing right here, well, that's the integral from A to B of f of x dx. This guy right here will give me this area. Then what I want to do is I want to take, oops, I meant to switch colors. I'm going to take the green guy. Okay. Between A and B, and I want to find the area underneath its curve and above the x-axis. And so these two guys added together, let's go like this, okay? These two guys together are given by the integral, let's call this g. So it's the integral from a to b of gx dx. Now, if I take the first guy and I subtract off the second guy, I get what's in between. So for example, if I take this guy and I overlap it here. Oh, that was bad. Let's try it again. Okay. So if I take the whole guy and I subtract off the green, what I get is the thing that I want, which is this thing in the middle. So the idea is to take from A to B, to take f of x dx and subtract off from A to B g of x dx. And that will equal the blue area, which is the region between the curves. That's what we want. Okay, so this, by the way, can be reduced or combined to f of x minus gx dx. Okay, so this is what we're looking for. Well, what we need to know, and probably the hardest thing about this section is to figure out where the curves intersect. So what I need to find, what is A and what is B. Because I'm going to have f of x and I'm going to have g of x. So what is A and what is B? Well, what I need to know is when is f of x equal to g of x. Because remember, f of x is the height of the yellow function and g of x is the height of the green function. So when are those two heights equal to one another? So we'll do that out and we'll see how far we get here. We've got f of x, which was equal to x plus 3. And we want to know when is that equal to g of x, which is the absolute value of 2x. And what we're going to do is we're going to use our definition of absolute value. Okay. So there's two cases for absolute value. Absolute value is either equal to itself or the negative of itself. So case 1 is that x plus 3 is equal to 2x. And case 2 is that x plus 3 is equal to negative 2x. So let's go ahead and solve this. We'll move the x over, so this will be x, subtract x from both sides, so x is equal to 3. Okay. Or we'll move this guy over, so this will be 3x. Something doesn't seem right there. What did I just do? I got x plus 3, subtract x from both sides, so I get 3. Okay, move this guy over this way. Oh no, I guess that's right. Move this guy over this way, move this guy over this way. So x is negative 1. So this guy must be negative 1, and this guy must be over at 3. So what do I want to find? Well, I'm looking for what is the integral from negative 1 to 3, okay, of f of x minus g of x dx. Here's the problem with this one though, is f of x is defined differently on both sides. So we don't have for g of x. For g of x, this green line right here, over here is defined as negative 2x, over here is defined as positive 2x, so I need to split from 0. So I can take this guy and I can go like this, from negative 1 to 0 of f of x minus gx dx, okay, and add to it from 0 to 3. You typically don't have to do this. This ugly piece right here is coming because of the way that we define the absolute value function. If it had been a different function, like let's say the squared function, x squared, we wouldn't have to do this separation. We would just go right here. Okay, so this is going to be this minus this, just like that. And the reason that we do that is because f of x, g of x takes on a different type of function depending on which side, which axis it's on, if it's on the positive x-axis or the negative x-axis. So let's go ahead and fill this stuff in. This is the integral. Actually, I'm going to go down one page here. This. Okay, so this guy is the integral of f of x, we know is x plus 3, minus, now g of x on this interval from -1 to 0 over here, this line is equivalent to -2x, which is what I did right over here. So it's equivalent to -2x. Now between 0 and 3, f of x is still x plus 3. Excuse me, g of x, though, is positive 2x. And now that should be clear if you look at the graph. G of x is taking on, right here, is taking on the form positive 2x. So I get this. So let's go ahead and do each of these separately. So we'll call this guy number 1, and we'll call this guy number 2. Sometimes you can combine these things back together, and sometimes you can't. So let's do number 1 over here. So number 1 is from -1 to 0. Of the quantity x plus 2x, so that's 3x plus 3 dx. Okay, and then we're going to add the integral from 0 to 3. Okay, now I've got x minus 2x, so that's negative x, so I'm just going to write this as 3 minus x dx. Let's work on this first guy over here. I want to find an antiderivative for 3x plus 3. And so that'll be 3x squared over 2 plus 3x, and evaluate that between -1 and 0. And then I want to add to that the antiderivative for this, which is going to be 3x minus x squared over 2 evaluated between 0 and 3. So let's do the blue one first. We plug in the 0 and we get 0, so this is going to be, I'll write the whole thing out for you. Okay, so there's that. Okay, minus this. Okay, then over here, that's going to be, let's see here, 3 times 3 minus 3 squared over 2 minus 3 times 0 minus 0 squared. Yeah, there it is. Over 2. Just like that. Okay, so let's go ahead and take a look at this guy over here. This is going to be 0. That's nice. Now minus, this guy's going to be a little bit more messy. -1 squared is 1 times 3 is 3 over 2, so this is 3 halves minus 3. Okay, over here, this is going to be 9 minus 9 halves minus 0. So we've got, this is going to be 3 minus 3 halves, just rotate the signs, plus 9 minus 9 halves. So let's put everything over 2. So this is going to be 6 halves minus 3 halves plus 18 halves minus 9 halves. So 6 minus 3 is 3. Okay. Plus 18 is 21. Minus 9 is 12, I believe. So it looks like 12 halves or 6. So let's go back and check our solution here. Okay. And if you walk through, you'll see that they split it up into 2 different regions. And what's cool here on this problem is they give you this nice bar underneath, and they rotate between these 2 functions, just like that. Okay, so they've got those 2 functions rotated between, and you'll notice that we get a value of 6 out. So I'm going to stop this video here. What I think would be a good idea is if you either work through some of the problems in your book, or you go look at some of the problems in the homework that are similar to this, and then what I'll do in the next video is I'll talk about how to integrate to find the region with respect to y instead of up and down with respect to x.